collection of forces and moments. And to be honest, there's not a whole lot of call for calculating these equivalent force moments. The concept is important. You have to know what it is, generally what it represents. But once we get through this beginning part of the course, we're not going to use it very much, if at all, past this point. Right now, it's as much to give you practice at calculating components of forces and calculating moments as it is for anything else. I guess before I erase this, I forgot to mention at the beginning of class. I wrote this up here before. This is the TA assigned to the class. So if you have difficulty getting me in my office, I'll need another person to talk to. You know, just want to talk to somebody else about these problems. That's another place that you can go. His office is right across the hall from mine on 2243. He's in 2242.
I hate limits.
Okay, one more two-dimensional equivalent force couple, and then I want to do a three-dimensional equivalent force couple. Actually, here we have a result. It says that we have this mechanism, this arm, which is acted on by two forces, a 400 Newton force and a 320 Newton force. In addition, we have a couple applied out here at the end. Now, the magnitude of the couple is not specified. This is the way I typically draw a couple. This is what it does. It causes a rotation. The author chose to draw as two forces, equal magnitude, opposite directions, some distance apart. How big are the two forces? Doesn't matter. What's the distance between them? Doesn't matter. All that matters is the product of force times distance, the tendency to rotate. We want to replace this with a single equivalent force couple at O. If the resultant of the two forces and couple M passes through point O, determine M. So I want to replace this with an equivalent force couple at O, which is going to have components OX, OY, and generally speaking, there would be a couple component of this equivalent force couple, but when it says the resultant passes through O, that says that the couple part is zero. The resultant is the simplest of all possible equivalent force couples. The simplest force couple is the one that has the couple be zero. Forces we can't do anything about. No matter what point we choose for an equivalent force couple, the X component forces is always the same, the Y component forces is always the same. The magnitude is always the same, the direction is always the same. The magnitude of the couple changes depending on where we find the equivalent force couple. So the simplest of all possible equivalent force couples is the one for which the couple is equal to zero. So this is the equivalent force couple at O, and it is the resultant if the couple comes out to be zero. So what magnitude of M will cause the total moment to be equal to zero? That's what it's really asking. So about this picture, the moment about O is simply equal to the couple. OX, OY have no moment. Therefore, the moment about O on this picture is going to have to be equal to zero. The moment about O on that picture is going to be M, that's what we're trying to find, minus, for the 400 Newton force, the moment is the magnitude of the force times the perpendicular distance between the line of action of the force and the point we're taking moments about. And that perpendicular distance is going to be 0.15 times the cosine of 30 degrees. Plus the moment of the 320 Newton force. The 400 is giving a clockwise rotation. I'm calling that negative. The 320 is going to give a clockwise rotation, also negative. So this is negative 320. Now I could find the x and y components of that 320 Newton force and take the moments of each component separately. But in fact, I'm told that this angle is 60 degrees, and that angle was given as 30 degrees, so that makes this force perpendicular to the arm. When we say moment equals force times distance, we have to make sure we're using the perpendicular distance. And in this case, the distance from O to the point where that force is applied is the perpendicular distance. So instead of dividing that into horizontal and vertical components, taking their moments separately, I'll just take the moment of the force directly. Why make extra work by dividing it into components? And that has to equal 0. Moment about O on the first picture, sum of moments about O on the second picture. And then it's just a matter of solve for M. M comes out to be 147.96 Newton meters. That much moment is required if the resultant passes through the origin of the coordinate system, point O. But whether we're doing equivalent force couples, resultants, we start with some forces. We want to replace them with a force and moment that has the same effect. Same sum of forces, same sum of moments on both pictures. I can draw another picture and say, well, it's equal to a force and moment at a different point, or a force and moment at a different point. Each of those would be an equivalent force couple. The simplest of all is the resultant. Let's do one in 3 dimensions. The first thing that happens in 3 dimensions, the forces get a little bit harder to write. In this case, it's not too bad because we're told that the 500-pound force is in the XZ plane. The 500-pound force has no Y component. So here is the original structure. I have a 400-pound force going backwards. I've got a 600-pound force coming straight down, and then I have this 500-pound force and those dotted lines are to say that the 500-pound force has a component in the X direction, the 500-pound force has a component in the Z direction. So it's in this XZ plane, but it has no Y component. It doesn't go in or out of that plane. I need to have a right-handed coordinate system if I want to use a cross product. So X rotating into Y with my right hand, my thumb should point in the Z direction. So X rotating into Y, the Y direction is going to have to go back into the plane as drawn on the figure here. So that's what we're starting with, and I want to determine the equivalent force couple at O at the bottom of that? Well, the equivalent force couple is going to have force components, Fx, Fy, and Fz. I want to choose the magnitudes of Fx, Fy, and Fz so that we have the same sum of forces, the same sum of moments on both pictures. In addition, I can have moments. I'll have a moment about the x-axis. I'll have a moment about the y-axis, and I'll have a moment about the z-axis. And for lack of any better choice, I've simply drawn all of these in positive coordinate directions. So Fx is in the plus x, Fy is in the plus y, Fz is in the plus z. For the moment about x, my right thumb points in the x direction, my fingers curl in the direction that it's going to make it want to rotate. For my, my thumb points in the y direction, my fingers curl in the direction it wants to rotate. For mz, my thumb points in the z direction, my fingers curl in the direction that that moment wants to make it rotate. If these are a truly equivalent, then the sum of forces in the x direction has to be the same on both pictures. The 400 has no x component. The 600 has no x component. The only force that has an x component is this 500, and its component is going to be 500 times the sine of 45 degrees. The angle in here was given as 45 degrees. So that comes out to be 353.6 pounds, and that's going to have to be the Fx of my equivalent force couple. That's the net total effect pushing it in the x direction. I'll do the same thing with the y direction. The 400 is in the y, 600 has no y component, the 500 has no y component. So the only force in the y direction is this 400-pound force, and it points in the positive y direction. So that's going to be the y component of my equivalent force couple. Z component, the 400 has no z component, the 600 is in the negative z, the 500 has a component in the negative z, that's going to be minus 500 cosine of 45 degrees. Those will add together to give negative 953.6 pounds, and that's going to have to be my Fc. So if I wanted to try to draw that, I would draw it as a force that has 353 in the plus x, would be 400 in the plus y. So those would add together to give me something like that. And then in addition, I have a force of 900 So adding the 900 with the sum of those first two is going to give me a force that looks something like this. It's going to go on the plus x, the plus y, and the negative z direction. Now the magnitude of that resultant force would be the square root of 353.6 squared plus 400 squared plus 953 squared. As far as direction, I can't conveniently describe that. I can give the angles with